one more example. An example to use the properties of the Fourier series transformation, like the differentiation or the integration. Let's do example 2. We have this signal. This is time. Here's the 0. Let's say this is called xt, and it's given this way. Yes. And so on. Periodic signal. We have here, this point is 1/2. This point is minus 1/2. And this point is 1. This point is minus 1. So this part of the signal, yeah, is given as 2t, right? When t equals minus half, the signal takes the value -1. When t equals 1/2, we get to 1. And this part of the signal, hello. This part of the signal is minus, because the slope is negative. So it's -2 t minus 1 was shifted by 1. So it's the same signal, minus, it changes the slope, flips the slope, and then we shift it by 1. Here, this is 1 here. So it's -2t minus 1, or we can write it as 2 times 1 minus t. 2 times 1 minus t. We need to find the Fourier series coefficients for this segment. One way to do it is, as we have been doing it so far, we just follow the equations. But first, we need to find the period and the frequency of the signal. What's the period of this signal? Hmm? What's the period of this signal?
It'd be 1. No, not 1. 1 and no, it'd be 2.
Should be 2.
Yeah, my
But,
bad.
yeah.
I'm having a brain fart while doing this.
It's okay. It starts from -1/2 to 3/2. This point is 3/2. Because also it's this climbing or this duration when it's climbing or growing is 1 and then falling 1. So the period T naught is 2, then the frequency omega naught is 2 pi divided by T naught, which is 2 pi divided by 2, which is 5. Do you feel happy when you see omega naught equals pi, as I do?
Yeah.
Yeah, it's a good number to see, especially when with those exponentials and Euler's formula. Yeah, so it's good. We have a frequency of angular frequency of pi. So this is pi radians per second. So every second, the signal will rotate by pi radians. So it will complete the circle, one rotation around the circle after 2 seconds, right? Right? If it rotates by pi every second, pi radians every second, then to rotate the 360 degrees or the 2 pi means 2 seconds, which is the period, 2 seconds.
Mm-hmm.
Yeah. So it needs 2 seconds to complete a rotation around the circle. And the speed is 5 radians per second. Now, if we want to do it, we start usually by the definition for the analysis equation, which is AK equals 1 divided by the fundamental period integral over 1 period xt exponential minus jk omega naught t dt. And then we substitute the period, we get 1 divided by 2, because the period is 2. And we need to decide the limits of the integration. We can do it from we can do it from here to here over 1 period. So from -1/2 to 3/2. From -1/2, 3/2 of xt exponential minus jk omega naught t dt. And over this period from -1/2 till 3/2, the function is defined piecewise. We have one piece, it's just 2t. The other piece is 2 times 1 minus t. So we can split that integral. This integral can be split into 2, and it will be 1/2 times. The first is from -1/2 till 1/2. So from -1/2 till 1/2. And the function over this period of time is just 2t times exponential minus jk omega naught t dt plus the rest is from 1/2 to 3/2. 1/2 to 3/2. And the function over this period was 2 times 1 minus t. So 2 times 1 minus t exponential minus jk omega naught t dt. theta. And we can do those two integrals, right? Those are not so hard to do, but we need to do integration by parts and integration by parts again here. Right?
Right.
We do the integration by parts here.
Yeah.
Then we find the AK. And from the equation that we will get, we can tell if k equals 0. If it doesn't go to infinity, then it's okay. It's good. So the AK that we find will be valid for all k values. But in this case, it will not. You need to find A0 alone, separately, I mean. Right? Because
Yeah.
when we do this integral, this jk omega naught will be in the denominator. So this k will be in the denominator. And I think it will not be valid for k equals 0. And then you need to find the A0 alone, separately, which is 1 divided by T naught, integration over T naught, xt dt. Because the exponential minus jk omega naught t will be 1. So we just have this, which is the average value of the signal. And by looking at the signal, you can tell, right, what's the average value of the signal. Can you see what's the average value of this signal? Mm.
No, it's not 0.
If you can look at the signal, it's just fluctuating around 0, like half.
I was going to say 0, but that
Yeah,
sounded kind of silly.
yeah, no, it's 0. It's 0. That's the correct answer.
Okay.
Because it's spending the same amount of time above 0 and below 0. And what's important is this area above 0 is the same area under the 0. So at the end, the average of this signal will be 0. So in other words, we say that this signal has no DC shift. So the DC component in the Fourier series of this signal will be 0. A0 will be 0, which is the DC component. There's no DC shift for this signal. It has 0 average value. Okay, we should do by parts over those two integrals to find the AK when k not equal 0, and when k equals 0, we find it separately, and we saw that it will be 0. And then AK will be, I'm just giving the answer if you wanna, and I would recommend also doing this, doing all the steps to verify. I'll just give the answer here. AK will be 0 when k equals 0. And it will be 4j divided by k pi squared when k is in plus minus 1, plus minus 5, and so on. 5, 9, 13, and so on. And it will be minus 4j divided by k pi squared when k is plus minus 3, 7, 11, and so on. the rest of the odd numbers. So all of the coefficients are odd, but they are split over two. One of them is just the negative of the other. The coefficients are just the odd coefficients are split in two parts. One of them is just the positive, the other one is negative, but all of them are odd. This is the long way. I wouldn't say the hard way to do it, but this is the long way to do this, to solve this. The easier way to do it is by using the fact or using the differentiation property, which says that if you have xt with ak coefficients, then the derivative of xt will have a coefficient multiplied by jk omega naught. We just multiply that coefficient by jk omega naught. If we take the derivative one more time, we multiply by jk omega naught again, so jk omega naught squared ak. And we will use this to solve this example, and it will be much easier than going this path. What will be the derivative of this segment? What's the derivative of this segment?
I'm tempted to say 0 again, but I don't want to look silly.
1 and 0.
Because like the first line, the red line, that like the derivative of that would be like 1, and then
It would be not 1. It would be the slope. The
oh, I
slope,
didn't see that 2t. My bad.
yeah, yeah.
Tunnel vision.
So the derivative will be just 2 over this period, because the slope of the function is 2, and the slope here is -2. So it would be 2 here, and then -2, and so on. It will be periodic also. Let me draw it here. The derivative uh, take derivative of xt for so this is the dxt dt, and it will be 2. This is 2 from -1/2 to 1/2, right? From -1/2 to 1/2. Mhm. -1/2, 1/2, and then it will be -2. My drawing is bad. I'll do it again. Let's see. So 3 -1/2 to 1/2. Is just 2. Let's move this one out of the way. And then from 1/2 to 3/2, it's -2. So -2. And it repeats. We'll have that 2 here, and then -2 here, and so on. will be minus 2 here, plus 2. So we can find the Fourier series for this one, right? If we find the Fourier series for this one, it's called BK. And then how to find the Fourier series of xt, the original signal. In terms of BK. How to do that? Using this property, we know that when we take the derivative, the new coefficients will be the original coefficients multiplied by jk omega naught. So if the coefficients of the derivative are bk, then ak, which are the coefficients of xt, will be bk divided by jk omega naught, right?
Yeah. Yeah, that makes sense.
We just to, because we know already that this bk is just ak multiplied by jk omega naught. We can from here find the bk, and then we will easily find ak from the Fourier series. But we can even make it simpler if we take the derivative one more time. If we take the derivative one more time for this signal, what we'll get?
It would just be squared, right? Or something.
No, I mean the signal, just the
Oh,
signal itself. What will happen to this signal if we take the derivative one more time to this?
it'd just be zero, right? Wait, no, why am I thinking that? Never mind.
It will be zero most of the time, but not always zero. The second derivative, like if we the derivative um, here it will be zero, right? And here will be zero. Here will be zero. Wherever the function is constant, the derivative is zero. But here, there's a change. There's a change. The function is jumping from 2 to minus 2. And here is jumping from minus 2 to 2. And the derivative, yes, here is 0, but here we have an infinite. The slope here is infinity, right? So at those discontinuities of the function, we'll have impulses. We'll have Dirac impulses. Here we have an impulse from, we are jumping from minus 2 to 2 instantly. So we'll have an impulse here scaled by 4, right?
Would it be negative or no?
No, the change, the rate of change is positive. We are moving from minus 2 to 2.
Oh,
We
right.
are increasing. At this edge, yes, it would be negative.
Mm-hmm.
At this edge, we fell from 2 till minus 2, so it will be like this, minus 4. and this at minus 1/2, and this one's at half, and so on. We'll have here again is a positive impulse, 4, and then -1. The scale is different. Let me- so this one is this one is this one is this one is this. And for this one, we're moving from 2 to -2, so it's a negative scale by -4, the impulse here. This is at -3/2. This is at 3/2. And this is at 1. This is 3, right? This should be 3. Right?
Right.
Mhm. Oh, this distance is longer than.
I'm so I'm going to have to leave right now because it's 7:37 right now and I'm going to need to do something.
Okay,
Uh,
no
yeah,
problem.
sorry about that.
Yeah, no worries, no worries.
Thank
All right,
you. Thank you.
thank you. So we have here 2 impulse trains. One of them is scaled by 4, the other one is scaled by -4. Here we have this is 4 delta t plus 1/2, shifted to the left by 1/2 and scaled by 4. This one is shifted to the right by 3/2 and scaled by 4, so it's 4 delta t minus 3/2. For the the other impulse train is -4 delta t plus 3/2, so shifted to the left by 3/2. This one is shifted to the right and scaled by -4, shifted to the right by 1/2, so t minus 1/2, and so on. Also, this impulse train will repeat similarly. We have here 2 impulse trains. Let's see, for the red one. So the red one is just a summation. One half, and then a 3/2, and then it will appear at and then so the distance between those two is from 1/2 to 3/2 is 2, and then from 3/2, if we add 2, 3/2 plus 2 will be 5/2, or 7/2, sorry. 7/2. We're adding, every time we're adding 4/2, or 2. The period is 2. So this can be written this way, or let's say we want to find the Fourier series coefficients of this signal. And we are looking at a period of this signal, which is just between -1/2 to 3/2. And between those 2 points, we have two impulses, one of them at -1/2 and the other one at 1/2. Which is for an impulse train. We know that the coefficients are just impulses and scaled by 1/T naught, which is in our case T naught, the period of this is just 2, so it's 1/2. So if we consider those two impulses or those two trains, one of them scaled by 4, the other one scaled by -4, and we know that the system is, or the Fourier series is linear. If we add those two and scale them by 4, we'll get the Fourier coefficients of the second derivative of xt, so the xt divided by dt squared. This will be 4 times half. This half is for an impulse train which starts at 0, the coefficient, but in our case, we have the impulses are shifted by half to the right and half to the left. So the ones that are shifted to the left, we multiply the coefficient by k omega naught times 1/2, which is the shift, the time shift from the time shifting properties of the Fourier series. And then the second half of the signal, which is the impulse train, that's scaled by -4, so we will have minus 1/2. Half is the T naught, sorry, the 2 is the T naught, and this will be also because of the impulse is time shifted by -2 for the exponential. We multiply in the Fourier or in the frequency domain by exponential j k omega naught times -1/2. And we know that also omega naught is pi. The signal after doing the derivative will remain have this period, the same period, and the same frequency. So the Fourier series coefficients of the second derivative of xt is written this way. Let me rewrite it in a clear way. D squared, or do second derivative of xt. We have those Fourier series coefficients, 4 times 1/2 exponential j k. Now instead of omega naught, I write pi divided by 2 minus 1/2 exponential minus j k pi divided by 2. Because here you have -1/2 and omega naught is pi. Okay. Now from Euler's formula, we know that this can be written as a sine, but what's missing here is the j term. So this can be written as 4 j sine, this is j sine k pi over 2. This is j sine k pi over 2 for j sine k pi over 2. Now to get back to xt, the coefficients of xt, we know that this is the coefficients of xt, but multiplied by jk omega naught twice, as we have seen here. So to get the AK, we need to divide the coefficients of this by jk omega naught square. So therefore, xt will have for we'll have those coefficients for j sine k pi over 2 divided by j k omega naught, which is pi. I write it now, or j k omega naught square, which is omega naught plus pi. So this is 4 j sine k pi over 2 divided by j square is just -1. We have negative here. K pi squared. Um, okay. Let's see, we have this first. Um, by noting that sine k pi over 2 is, let's say for k equals 0, sine would be 1, and then we'll have here infinity. So this will not work for k equals 0. We need to calculate k equals 0 separately, which we have found that it's 0 already. Now, when k equals, let's say 1, we'll have sine pi over 2. And the sine this is pi over 2. And the sine is 1. And when k equals 3, will be at this point, and this will be -1. So on the when k equals 1, we'll have positive 1 here. When equals 3, we have negative. When k equals 4, 5, when k equals 5, we get +1 again. When k equals 7, we get -1, and so on. So if we take this into account, we'll be able to write the coefficients this way. For j, when k is 1, 5, 9, and so on, we get a positive term in the sign. The sign will be +1. And when we have the rest of the odd numbers, we get a -1, and then the negative will cancel with this negative, and we get 4j divided by k pi squared. Yeah. And that's all for today. I have done this one quickly at the end, since we're running out of time. We're already recording for now 2 hours almost. So I'd encourage you to do this again, step by step, and we might also discuss it again in the next workshop. Thank you.